In this video revision lesson, we will be solving some past exam revision questions on paper 2. You know, this paper 2 is divided into 3 sections. Section A is on physical chemistry. Section B on inorganic chemistry, and section C on organic chemistry. But because of the limitation of time, we are going to treat these 3 sections independently. And today, we will be starting with section C, which is the organic chemistry part of it. Before we continue, I really want to appreciate those of you who have subscribed to our channel. Once more, thank you for a job well done. We will really appreciate more of your comments. But to motivate us to keep on assisting you in your studies, please like the video, share, comment, and most importantly, subscribe to our channel. Thank you. Welcome. We want to continue today with the organic chemistry part of our questions. This is a Cameroon GCE A-level chemistry, organic chemistry section of the exam. It is paper 2, structured questions. I apologize for the poor quality of the question paper. We're starting with number 5, question number 5. This is June 2020. Question number 5. This question relates to organic compounds and their reactions. An organic compound A contains hydrogen, carbon, chlorine, and a double bond. A. How would you identify the presence of 1. A double bond? Yes, this is an unsaturated compound. This is an unsaturated compound. To identify a double bond in an organic compound, there are 2 methods. You can either use bromine water test, or you use Bayer's reagent. I will start with number 1. I will start with the first one, which I said bromine water. I said bromine water test. Bromine water test. Bromine water test. Bromine water test. Under this bromine water test, this is what you write. The first thing is bromine water test, because you state your main point before you can give the explanation, because some students are not very good in trying to describe something. So examiners are interested in the major points. bromine water test. Okay, you can now say add bromine water containing tetrachloromethane. You can add bromine water containing tetrachloromethane, which is Cl4. Add bromine water containing tetrachloromethane to an unsaturated compound. If the orange color disappears, then it contains a double bond. That is just all. If you add bromine water to an unsaturated compound, it does what? The brown the orange color will disappear, indicating the presence of a double bond. Or you can say bromine water, the double bond, it decolorizes bromine water. That's just all. Any organic compound containing a double bond will decolorize bromine water. So if you add bromine water to any organic compound containing a double bond, the orange color disappears, indicating the presence of a double bond. Another method is the Bayer's reagent. Bayer's reagent. You can use the first one or you use the second one, Bayer's reagent. With Bayer's reagent, if there is a double bond, the color of the solution will change to brown. Write Bayer's reagent. Then you can state there, on addition of Bayer's reagent to an organic compound containing a double bond, the color will change to brown. Finish. There are 4 questions there. There are 4 marks. The other one is chlorine. How will you identify the presence of chlorine in an organic compound? This organic compound here, the organic compound that you were given, how will you identify chlorine? You know that for halides, you want to identify the halide ion, like the chloride ion, the bromide ion, the iodide ion. There is a common reagent that we usually use, and that one we call it silver nitrate test. A silver nitrate solution. If you add a silver nitrate solution to any substance containing any halide, if you add it to any substance containing chlorine, if you add it to any substance containing bromine, they are going to be precipitates that are formed. But in this case, this is an organic compound containing chlorine. We can now say addition of a freshly prepared, the first thing you write there is silver mirror test. Use silver mirror test. The main point. Use silver mirror test. Then you can describe. On addition of a freshly prepared solution of silver nitrate, excuse me, please. Sorry. Silver nitrate, sorry. Use silver nitrate test. When you write use silver nitrate test, you cannot proceed. On addition of a freshly prepared solution of silver nitrate to a sample of organic compound containing chlorine, the presence of chlorine there is indicated by the formation of white precipitate. So if you add this on addition of this to any solution, you will see that silver nitrate will give this ion, silver nitrate, this ion plus is aqueous plus the chloride ion. There will be a silver chloride, which is solid, formed as precipitate. So, how to identify the presence of chlorine? You will now say use silver nitrate test. Then you can describe addition of solution of silver nitrate to a sample of organic compound containing chlorine. The presence of chlorine is indicated by the formation of white precipitate. We call it white precipitate. These are white precipitate. White precipitate that are formed. These are white precipitate. So, any organic compound containing chlorine, if you add a freshly prepared silver nitrate solution to it, the presence of chlorine there is indicated by the formation of white precipitate of silver chloride. That is just all. It takes us to the B part of it. It has to do with calculations. The B part of it has to do with calculations. And we are told if 0.485 gram of the compound A contains 0.120 gram of carbon, 0.01 gram of hydrogen, calculate the empirical formula of the compound. Okay. The empirical formula of this compound. This is an organic compound that you have been given. They want you to calculate the empirical formula. Okay, calculating empirical formula for this compound, the first thing you will do here will be, they say the compound contains carbon. The compound contains carbon, hydrogen. It contains carbon, hydrogen, and chlorine. Carbon, hydrogen, and chlorine. And their masses are carbon is 0.12, 0.12 gram. Hydrogen is 0.01 gram. And chlorine, we were not given chlorine. But remember, they said 0.48 gram of G of A contains this, and that. If we add all this, it is not up to this. It is not up to 0.485. And we were told the organic compound contains, from up here, the organic compound contains hydrogen, carbon, and chlorine. Therefore, the last one is chlorine. And in order to have the last one, it will be 0.485 minus this minus 0.120 gram and 0.01 gram. And the difference there, you add this, the difference there will be 0.355 gram. It will be 0.355 gram. Okay, now that is the mass. This is the mass. We can say this is mass. That is the mass. Okay, we want to have the moles of this. The moles, the number of moles. You are given a formula. The formula is to have the number of moles of a particular substance, you will divide the given mass by its the relative atomic mass. And the relative atomic mass for carbon is 12. So now, the relative atomic mass for carbon is 12. So our number of moles will be 0.120 gram divided by 12, 0.01 gram divided by, for hydrogen it is 1, And for chlorine is 0.355 gram divided by 35.5 gram per mole. All these are gram per mole, gram per mole, gram per mole. So that the gram will cancel per gram and we will be left with the moles. And the number of moles here, if we do this division, our number of moles for carbon will be 0.01. Our number of moles for this other one here will be 0.01. And the number of moles of this one here will be, that is 0.355 gram divided by 35 point this, we will have 0.01 or 0.01. Now we divide by the, and all are the same, so we have 1, 1, and 1, and this gives us what? It makes us to be our empirical formula will be what? Our empirical formula in this case, empirical formula will be will have what? Will have carbon, hydrogen, and chlorine. That will be our empirical formula. So our empirical formula after the calculation, we will have only we will have carbon, hydrogen, and chlorine. That will be our empirical formula. That will be our empirical formula. Now, it takes us, that is the answer. It takes us to the other section. We are told empirical formula, that is the one. Then 2, 0.4 gram, 0.485 gram of compound A reacted completely with 1.7 gram of silver nitrate in the ratio 1:2. The molar mass of silver nitrate is 170 gram per mole. Determine the molecular mass of A. Yeah. To determine the molecular mass of this, okay, we have two. We have been told a reacted at a reacted. Okay, 2. The 2 part of it is 2 moles of silver. We have been given the mass of silver to be 1.7 this silver nitrate. So the number of moles of silver, you have been given the mass. Make use of the information you are given on your question paper, please. So now you have been given the number of moles, you have been given the mass of the organic compound, which is of A, and you have been given the mass of silver nitrate. You have been given the mole ratio that they reacted with A. Now, and you have been given the MR, or we call it the molar mass of silver nitrate. So, in order to have the molar mass of A, what do we do? First of all, make use of this information. Moles of silver nitrate. We'll now say the moles of silver nitrate. The mass of silver nitrate was what? 1.7 gram divided by what? By the molar mass of silver nitrate is 170 gram per mole. And the number of moles of silver nitrate will be what? The number of moles of silver nitrate will be 0.01. It will be 0.01. That's the number of moles of silver nitrate. But remember, we were told they reacted in the ratio that is A. We were told that A plus silver nitrate silver nitrate in the ratio what? In the ratio 1:2. 1, 2, 2. Okay, we want to make use of this information. We can now say, if simple proportion, if 2 moles here, 2 moles of silver nitrate can react with 1 mole of A. If two moles silver nitrate react with 1 mole of A, then the number of moles of silver nitrate we got here was what? 0.01. Then therefore 0.01 moles of silver nitrate will react with X of A. Now, what will be the value of X? The value of X will be what? X, the number of moles of A that will react will be what? The number of moles of A will be what? The moles of A will be 0.01 times 1 divided by 2. And the number of moles of A will be what? The number of moles of A will be 0. The number of moles of A will be what? 0.005 moles A of the organic compound A. That will be the number of moles of A that will react. That will be the number of moles of A that will react. Having got those number of moles of A, remember in stoichiometry, when we are calculating the number of moles. Now, when you have the number of moles of a particular substance, to have the mass of that substance will do what? Remember, remember from our expression moles. Remember moles. Moles is equals to what? Mass divided by molar mass. Molar mass, or what we call, you can call it ml. You can use this expression. If you use this expression and rearrange it, you will have everything. That is moles equal to mass all over molar mass. If we use this expression, you will see that if we arrange all this, the mass will be what? The mass will be equals to the mass or the molar mass. So we are looking for the molar mass. We have been asked to look for the molar mass. The molar mass the molar mass will now be equals to molar mass. So I say moles equals to mass divided by molar mass. Molar mass, rearranging it, the molar mass, which is mr, will be equal to the mass divided by what? Divided by the number of moles. And when we do that, substituting our value, our mass of A, we're given that A has a mass of 0.485. The mass of A is 0.485 gram. And the moles of A that we calculated, is what? Is 0.005 moles. So now our molar mass will be what? Our molar mass, if we divide this by this, our molar mass will be 97 gram, because it is gram divided by moles, gram per mole. That will be our molar mass, uh, mr of A. That is the molar mass of A. mr is another short form for molar mass. mr of A will be 97 gram per mole. That is our answer, 97 gram per mole. So we can say the molar mass, the molar mass of A, the molar mass of A, the molar mass of A is 97, 97, sorry, the molar mass of A is 97. Is 97 gram per mole. 97 gram per mole. You have seen the calculation here. Then the molecular formula of A, that is the B part of it. Molecular formula of A. How can we give the molecular formula of A? The molecular formula of A will definitely be molecular formula of A. Now, to have the molecular formula, that is the B part of it, B part of it, which is the molecular formula, molecular formula of compound A. Now you have the molecular formula. So now what you will do will be, in order to calculate the molecular formula, we will say the empirical formula, which is the CHCl. The full molecular formula is supposed to have the molecular mass is equal to be the molecular mass. If we add all the related atomic masses in the molecular formula, it's supposed to be equal to the molecular mass. So now, if we add this is supposed to be equal to what? It's equal to what? It's equal to the molecular mass. Molecular or molar mass is supposed to be equal to the molar mass. Okay, molar is equal to the molar mass. And this will be CHCl is equal to what? 97. Equal to 97. Equal to 97, which is the molar mass. But if we add all these, we add the relative atomic mass of carbon, hydrogen, and chlorine, it cannot be up to this. Therefore, we now say there is a certain number. If we add all these, there is a certain number. We add all these, will be equal to that. Let's solve for the value of n. And in order to solve for this value, what we will do here will be, we will have, if we add this, the related atomic number for carbon is 12. 12 plus 1 for oxygen, that is 13. Then 13 plus chlorine is 35.5. Chlorine is 35.5. If we add all this, it will be equals to 48.5. That will be equals to 48.5 n equals to 97. And what will be the value? The value of n will be equals to what? 2. The value of n will be equal to 2. And if we now substituting 2 in our in this, substituting 2 it will give us, substituting to our molecular formula, substituting to our final molecular formula for the compound will be 2. If n is equal to 2, 2 times C will be C2. Okay, 2 times H will be equal to H2. Okay, 2 times Cl will be equal to Cl2. And this will be our molecular formula. That will be our molecular formula. So now our molecular formula for this, will be C2, H5, and a Cl2. Then we are told give two. This is already an alkene. Give two isomers of compound A. Okay, isomers compound A. What are the isomers of compound A? What are isomers? Isomers, they have the same molecular formula but different structural arrangement. So now, molecular formula, they have the same molecular formula, which is C2, C2H2, Cl2, but different structural arrangement. So the isomers here will be what? Since there are two, we will say it is carbon, carbon. Give two isomers. Isomers of this compound. Isomers of A. Isomers of A. Now, for an alkene, it has a double bond. Alkene must have a double bond, and we're told in the answer the compound has a double bond. This is it here. From the onset, they say carbon, hydrogen, carbon, chlorine, and a double bond. So there are two atoms, since there are two carbon there, we will now say we have a carbon, double, there are only two carbons, so it will be a double bond, a carbon, carbon, a carbon, carbon. Then we have a hydrogen. Now, there is one hydrogen here. You can see one hydrogen is here. You can see it here, hydrogen. And there is another hydrogen here. And there are two chlorines. We can now say this is chlorine. This is chlorine here. We can say this is chlorine here. And this is another chlorine here. We can rearrange this again and say this is how it is. We have carbon, carbon. There's carbon, carbon. And we have, this is a hydrogen. And this is another hydrogen. Hydrogen are on one side. Then chlorine on this other side is on the other side. Chlorine and chlorine. Remember, when we're doing isomerism, this is a stereoisomer. There are two types of stereoisomers. We have geometric isomerism and there's optical isomerism. Here, there is no optical property here. So what is here is geometric. This is a geometric isomer. And geometric isomer is as a result of non-rotation about the carbon-carbon bond. The carbon-carbon bond cannot rotate. It cannot rotate. That is why it results in isomers. Okay, difficulty for the carbon term there's a difficulty for the carbon double bond to rotate. So that's why this results in isomer. And we said there are two types of geometric isomerism. We have the cis and the trans. Cis, that is, you see across the double bond, that is trans. On one side of the double bond, there is cis. So we now call this one trans isomer because chlorine and chlorine are across on the different side. So we now call this trans isomer. This is a trans isomer. And since chlorine and chlorine and hydrogen are on one side, on two different sides, we now say we call this cis. This is a cis isomer. This is a cis isomer. So there are two types of isomer here. We have one. This is the first one that I have given here, which is the trans isomer. This is the trans isomer, which is one. And the second one is the cis isomer of the compound. So if you did this, you are likely going to have all your marks. If you did this, you are likely going to have all your marks. So now it takes us to the last section, we are done with section C. Give two isomers. That is 2 marks. One isomer is 1 mark, and the other isomer is 1 mark. So please, that is what you are supposed to do. Once more, as I said, you need to make use of your information. You need to make use of your information. You calculate the relative, the empirical formula using the mass divided by the molar, by the relative atomic masses, and then you divide by the smallest, and you have your empirical formula. You are given the mass and the relative, the mass and the molar mass of silver nitrate. You divide the mass by the molar mass of silver nitrate. You have the number of moles of silver nitrate, and they say it was reacted in the ratio 1:2. The mole ratio is one of the organic compound reacting with 2 moles of silver nitrate. You take a simple proportion for you to better understand. If 2 moles of silver nitrate can react with 1 mole of A, then the number of moles of the silver nitrate we calculated will react with how many moles of the organic compound A. We calculated it, and we saw that our number of moles of A is 0.05. Now, a relation says moles equals to mass all over the molar mass. Now we rearrange it to have the molar mass because we have been told to look for the molar mass. Now the molar mass here, after rearranging this formula here, the molar mass will be what? Will be mass divided by number of moles, and if we divide that, we will have 97 grams per mole, which is the molar mass of A. Now that is the molar mass of A. We are told to look for the molecular formula of A. Now, when you add all the relative atomic masses of all the elements present in the compound, you will have the molar mass. But when we add this is an empirical formula. This is an empirical formula. It does not contain that. So we need to multiply it by a certain factor that will give all the molar mass. So the factor is n. And when we solve for n, we saw that n is equal to 2. And if we substitute n in this equation, in this formula here, our formula mass will be C2H2Cl2. When we do that, that will be the formula mass of the compound. That will be the formula mass. Now, isomers, since they say the compound has a double bond, so it is an alkene. It's a chloroalkene. So in this case, what we usually do for this compound, we can say it is 1,2-dichloroethane. 1,2-dichloroethane. So now, this other one to so now we have a trans and the cis because of what? Only alkenes or trans and the cis isomer only exist in compound containing double bonds. And why so? I said double bond exists here as a result of non-rotation about the carbon-carbon double bond. That's why isomers exist in alkene, because what? There's no rotation about the carbon-carbon double bond. It took us to the second part of the equation that has to do with the amines. The amines, we are told that amines here are, they say, complete the table below. D part, D1. Complete the table below, giving the structure and the name of primary, secondary, and tertiary amine with molecular formula C3H9. Okay, you know that amines, they have NH2. So to have a primary amine, remember that an amine this is how you can look for amine by substituting ammonia. That is, ammonia molecule is like this. There is ammonia molecule. So it has a double bond there. So now if we substitute one amine, we will have this. If we substitute one amine for the hydrogen of this, we will have N. It will be N. Let me say we substitute one amine here. Okay, if I substitute this one here, if I substitute this here by an alkyl group or by an aryl group, alkyl are these are long chain or branch chain molecules. Then alkyl groups, we are talking of aromatic groups. If I do this here, let me say R1, that is, we now call this a primary amine. If I say substitute the next hydrogen by substituting the next hydrogen, I will call it, that is nitrogen here. Okay. If I substitute the next hydrogen on the ammonia, that is R1, then I substitute it by R2. Now, this is a secondary amine. Now, if I substitute the third hydrogen, like this one, this is R1, no, this is R1, R2, and R3. So all this is a tertiary amine. This is a secondary amine. So by substituting the number of hydrogens on the ammonia molecule, it gives you the type of amine you have. So now by substituting one, we have a primary. R could be a methyl group. R could be this methyl group. R could be a methyl group. R could be an ethyl group. It could be an ethyl group. R could be a propyl group. R could be a butyl group. So any alkyl group will if any alkyl group substitute this one, it will give you a different amine group. So now by substituting one hydrogen here by R1, it could be a methyl group, it could be an ethyl group. We have a primary amine. By substituting two hydrogen, we have secondary amine. By substituting all the hydrogen, we will now have a tertiary amine. An example of this, if we substitute this, for example, and say this is this, and we now have NH2, like in this case here, like in the first case here, we have substituted this one. In the first case here, we have substituted this arrow here by a methyl group. We will have NH2. And the NH2, we call it methylamine. This is a methyl group, methylamine. If it was an ethyl group there, we will call it ethylamine. So now, if we substitute 3 in that order, So now going back to our formula, to our question. Going back to our question, they said, going back to our question, okay, we were given CN. We were given C3H9N. C3H9N, C3H9N, and N. And we are told to do what? Primary, secondary, and tertiary. Okay, this is the formula. Now, the first one for primary is what? For primary, we need to have only one hydrogen that is being substituted. So for primary, what we will have will be, it will be nitrogen, hydrogen, and hydrogen. Then this one will be what? Now, this one will be what? It will be an this one will be a propyl group. 3 carbons must be here in order to fulfill this condition. The 3 carbons must be there. So the 3 carbons here will be what? We will have a carbon, a carbon, a carbon. You see it? 1, 2, 3, these are hydrogens, hydrogens, hydrogen, 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 hydrogen. Now, C3, 1, 2, 3. For hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9. We now have our hydrogen. So we can now summarizingly say our compound is CH3, CH3, CH2, CH2, what? We can say NH2. That is our propyl, that is our primary amine. And that primary amine, the name is what? The primary amine, the name is, we say the structure is CH3, CH3, CH2, 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 NH2. Because only one of the hydrogen has been substituted. So we call it a primary amine. And what will be the name? The name here is 1. The alkyl group is 1, 2, 3. There are 3 carbons. So we call it a propyl. Propyl is 3. So we call it propylamine. We call it propyl. So now, if we go again and we do our substitution again. If we go again and do our substitution for the next carbon, let's say we want to do for the next carbon, which is, we want to substitute for another carbon here. So in that case, we will have, this one here. In that case, we will have yes, and we want to substitute hydrogen here in order to give us we want to substitute 2 hydrogen now. So we let's substitute 2 hydrogen with a methyl group. I mean with a methyl group. Let me say a C. Okay, hydrogen, hydrogen, another hydrogen. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So our this other formula here will be a CH3, CH2, CH3, CH2. Since there is a methyl group here, we can say bracket CH3 NH. So now the name of our formula will now be equals to what? If we write it here, we will have a CH3, a CH3, a CH2, a bracket CH3, then NH, and we'll call it ethyl methylamine. Ethyl methylamine. Ethyl methylamine. So now, if we substitute the last hydrogen, let's say we want to substitute the last hydrogen so that we can have a tertiary amine. What we will do will be this. We are going to substitute all with methyl groups. So now this will be a methyl group. Now we want to substitute this other hydrogen here with a methyl group. We want to substitute hydrogen here with a methyl group. So what we will do will be, with a methyl group here, what we are going to do here will be, we'll put a methyl group. There will be a carbon, hydrogen, hydrogen, and another hydrogen. So now, the formula of our compound, the formula of this compound here will be a CH3. Yeah, we can still write it this way. We can say it is nitrogen, CH3, CH3, and a CH3. Where we can summarize it and put it as, there are 3 methyl groups. So we can say CH3 in bracket 3 and a nitrogen. That is a tertiary amine. And we can put it in our question paper on our answer sheet as CH3, CH3 bracket 3 and nitrogen. And in naming it, we can now say it is trimethylamine. Trimethylamine or amine. Trimethylamine. So you can put it like that. Okay. It takes us to the D2 part of the question. The D2 part of the question, after knowing this, the D2 part of the question. Okay. The D2 part of the question. Okay. Primary amines can be prepared from amides by Hofmann's degradation. Primary amine can be prepared from amides by Hofmann degradation. Write a general equation for this. There are many ways of preparing primary amines. The examiner has asked us to use but Hofmann degradation. And with Hofmann degradation, we have the reagent, which is Hofmann degradation, we have the reagent. And the reagent is a strong aqueous sodium hydroxide or potassium hydroxide. That is a strong alkali. Reagent is a strong alkali reagent. It's a strong alkali, which it could be strong aqueous. It's a strong aqueous sodium hydroxide or potassium hydroxide and a halogen and a halogen and a halogen. The halogen could be bromine, it could be chlorine or bromine. So we will have a strong aqueous sodium hydroxide or potassium hydroxide and chlorine or bromine. And now we will have to heat it. We will have to heat it at about 70 degrees Celsius. We will heat it about 70 degrees Celsius. And our equation will be what? We will have this. For the Hofmann degradation, this is what we will have. Using this, we will have the arrow represent the alkyl group. That then an amide has a carbonyl group there, and an amine group. That is an amide. So now when we heat this on the amide, now we will have a primary amine. The primary amine will be we call it the primary amine because only one hydrogen has been substituted from the ammonia. That's why you see arrow dash NH2 plus a carbon dioxide is released. A carbon dioxide is released. But the conditions are what? I told you that on the equation you will say bromine. When you heat an amide with bromine, you could bromine, yeah, let's choose bromine. Bromine in heat an amide with bromine in aqueous sodium hydroxide. This aqueous, I'm putting water here for aqueous. Okay. So now the equation is the amide contains a carbonyl group. Then with the amine group, the amine group. So you now heat the amide in bromine. Heat it with bromine in aqueous sodium hydroxide. You could see say aqueous potassium hydroxide. And you have a primary amine and carbon dioxide is being released. So that is just what you do. So the condition is a strong aqueous sodium hydroxide, or potassium hydroxide, and bromine or chlorine. That's just all. Then heat it to about 70 degrees Celsius. And this is the general equation. That's what you are supposed to do. But remember that for the purpose of revision, you can still produce amide by reduction. You can still produce amide through through reduction process. This one is just for revision. It is not for the answer. This is the answer for our equation. Hoffman degradation in ammonia with ammonia, with bromine in aqueous sodium hydroxide. But for purpose of revision, for purpose of revision, you could still produce it by reduction using lithium tetrahydroaluminate in dry ether. In that case, this will be the equation. You will have the amide. You have the amide. This is the amide. It will give you a primary, we'll have amide plus these 4 hydrogen have been donated by lithium tetrahydroaluminate. This is what you will have. CH2, NH2 plus water. And the condition here is that it is reduction. You are going to use lithium tetrahydroaluminate. You are going to use this, and this process is called reduction. Reduction, you are adding hydrogen, because hydrogen is provided by lithium tetrahydroaluminate. So the 4 hydrogen are added here. The hydrogen will enable you to have a molecule of water, and will enable you to have to convert this carbon to CH2. So this is another method, is method 2 by reduction, but it is not involved in our answer. It is not involved in our answer, please. It's just for the purpose of revision. It's for the purpose of revision. So our answer is a strong aqueous sodium hydroxide or potassium hydroxide and a halogen. So you heat an amide with a halogen, which is bromine, in a strong potassium hydroxide. And this is the equation. This is the equation. You give that, you are fine. You can put it here like this. Hoffman, that is a part of it. You can put it as arrow. Yeah. Mine. You have arrow. And what you will put here will be bromine in sodium hydroxide, bromine in aqueous sodium hydroxide. That is, you can put water there. Yeah. So this is the equation, the amide, this, yeah, to give you a primary amide. Okay. It takes us to give reagent and reaction condition. We are already given that. I said the reagent is a strong aqueous sodium hydroxide and bromine. The condition, you heat it to about 70 degrees Celsius. Now, what feature of amine is responsible for their being basic? The feature of amine that is responsible for their being basic. Okay. The feature of amine that is responsible for their being basic is this one. For amine to be basic, amines will only act as basis because of what? I told you that amine, look at the structure of the amine. Let me say this. Nitrogen. I said Nitrogen has a lone pair on it. So, what feature of amine that will make them being basic? I say the feature of amine that makes them basic is, excuse me, because of the presence of the lone pair of electron on the nitrogen atom. Because of the presence of the lone pair of electrons, lone pair of electron on the nitrogen atom. That is the only feature that makes amine to be basic, because of the presence of the lone pair of electrons on the nitrogen atom. For the purpose of revision, let me give the reason. Remember, a base is a proton acceptor. A base is a proton acceptor, and an acid is a proton donor. Since a base is a proton acceptor, it must have this lone pair of electron to donate to the hydrogen ion to form a coordinate bond. So all bases must have a lone pair of electron to donate to form a coordinate bond with a hydrogen ion that comes in. So any hydrogen ion that is coming in, for instance, let's say this is a hydrogen ion that is coming in. It does what? The base must donate the lone pair of electron to it. So the feature of the main characteristic, or the main feature that makes amine to be basic, is the presence of the lone pair of electron, That's just all. I'm not giving this reason for the purpose of revision, that a base is a proton acceptor. It is a proton acceptor because it donates its lone pair of electron to the hydrogen ion, forming a coordinate bond. And an example of this is, let me say this is an amine. For example, this amine here, Ag, we have this amine, NH2, with the lone pair of electron here. It will react with incoming hydrogen ion to do what? It will react with incoming hydrogen ion by donating a lone pair of electron to this hydrogen ion. It will donate the lone pair of electron to the hydrogen ion, and the bond form will be what? It will be a coordinate bond. It will be arrow, because this one will attach itself here. So that property is the presence of the hydrogen, the presence of the lone pair of electron on the nitrogen atom. It takes us to suggest this one. So presence, what feature of amine is responsible for being basic? I have already mentioned it, the presence of lone pair of electron. The presence of lone pair of electrons on the nitrogen atom. Presence of lone pair of electrons on the nitrogen atom suggests one way of increasing the basicity of an amine. That was June 2020. Suggests one way of increasing the basicity of an amine. Okay, how can you increase the basicity of amine? The thing is this: how can you, the basicity of amine will depend on the availability. It will depend on the availability of the lone pair of electron. The only way you can make the lone pair of electron on nitrogen available for bonding, that is increasing the basicity. So the first reason we will give here will be, what? One, by making available the lone pair of electron on the nitrogen atom to bond with this? One, by making available the lone pair of electrons, the lone pair of electrons on the nitrogen atom to bond with hydrogen. On the nitrogen atom to bond with hydrogen ion. So by making available the lone pair of electrons on the nitrogen atom to bond with this. Or you can say, or alternatively, you can say, the way you can increase the basicity, you can say by increasing the number of alkyl groups or electron donating groups on the nitrogen atom. That's all. By increasing the number of alkyl groups. The alkyl groups, we call them electron donating groups. Electron donating group on the nitrogen. On the nitrogen. This has a positive inductive effect. This has a positive inductive effect, making the electrons readily available to bond with in that case, primary amine are less basic than secondary amine. And secondary amine are less basic than tertiary amine. So, which one is the strongest? The strongest base is the tertiary amine. Tertiary is stronger than secondary, and the secondary is stronger than primary. And primary is stronger than ammonia. So we are saying that the only way to make the basicity, to increase the basicity of an amine, is by increasing the number of alkyl groups or electron donating groups. For instance, I said this is an amine. This is an amine. Let's say this is a methyl group, this is a methyl group, and this is a methyl group. Remember that these are electron donating. Okay, I take another example, like this is an amine here. So this is a tertiary amine and this is only a primary amine. Now these are electron donating. All these alkyl groups, they are donating electron on the nitrogen. They are increasing they are increasing the number of electrons on nitrogen, and they're making electrons available for bonding. They are making electrons available for nitrogen to give out to form coordinate bond. And when you form a coordinate bond by donating a lone pair of electrons, you are more basic. That is a basic characteristic. So three different electron donating group will increase more number of electron on the nitrogen atom than only one electron donating group or one alkyl group. So in that case, tertiary amine are more basic than primary amine because there are more electrons that are being donated to the nitrogen, making the electron more available for bonding with hydrogen ion than in the case of a primary amine. In that case, we are concluding that the basicity of amine can be increased by increasing the number of alkyl groups or electron donating groups on the nitrogen. This has a positive inductive effect, making electrons readily available to bond with hydrogen. Again, for you, you can state briefly, if you cannot explain, you can say by making available the lone pair of electron on the nitrogen to bond with hydrogen ion. That is just all. By doing that, I think we are done with only one question. We will go back, we will be starting with the other question on this topic. So once more, this is June 2020. This is June 2020, question number 5 of the Cameroon GCE A-level chemistry syllabus, section C on organic chemistry. We have answered the first question that has to do with double bond using bromine water or bias reagent. Then the second question that has to identify chlorine by using a silver nitrate solution, a freshly prepared silver nitrate solution. And identification is the formation of white precipitate of silver chloride. Then we went into stoichiometry by calculating the empirical formula for the compound, using the empirical formula, using the information that was given, and then we calculated the moles of, we calculated the number of moles of silver nitrate, using the number of moles of silver nitrate, the number of moles of silver nitrate, and the mole ratio to calculate the number of moles of of organic compound. We use the number of moles of organic compound to calculate the molar mass by dividing the mass by the number of moles. We have the molar mass. We use the molar mass and the empirical formula to calculate the formula mass of the compound. And we use the formula mass of the compound to calculate, or the molecular formula, to calculate, to come out with isomers that are being formed by this compound. It's an alkene. The isomers, we notice that it was only one type of isomer, which is geometric isomerism, the cis and trans isomers that resulted from that. Then we went further on amines. How to identify a primary amine by substituting alkyl groups on by substituting the hydrogens on ammonia. And when you substitute one hydrogen, you form a primary amine. Two hydrogen atoms substituted by different alkyl groups will form a secondary. And when the three hydrogen on the ammonia is substituted, we form a tertiary amine. In that case, we're given C3H9N to come out to deduce the different classes of amine that this compound can form. We came out with propylamine, ethylmethylamine, and the trimethylamine. And I gave the structures here, you saw them. Then how primary amine can be prepared using Hofmann degradation. I gave an equation of an amide that is being heated with bromine in aqueous, a strong aqueous sodium hydroxide or potassium hydroxide. And a primary amine is formed and a release of carbon dioxide. I went further and said they could also be produced through a reduction process using lithium tetrahydroaluminate. But that is not involved in the answer. It's for the purpose of revision. So I went further and I said what features of amine is responsible for their being basic. I said that the condition that make amine to be basic is the presence of the lone pair of electron on the nitrogen atom. Bases are proton acceptors. By doing what? They accept proton by donating the lone pair of electron to the proton. That is, they donate the lone pair of electron to the hydrogen ion, and thus forming a coordinate bond or additive covalent bond. And I did that here. So the presence of the lone pair of electron on the nitrogen makes them to be basic. Then we went further to say, suggest one way of increasing the basicity of an amine. And one way of increasing the basicity of amine, I said there are two ways. By making available the lone pair of electrons on the nitrogen to bond with hydrogen ion. So as far as available as the lone pair of electrons are there for coordinate bonding, that is a reason. So you can go further to explain that by increasing the number of alkyl groups or electron donating groups on the nitrogen atom. By doing this, so if you increase them by substituting the hydrogen on the ammonia, we increase it from primary, secondary, and tertiary amine. This electron donating group help to donate electron on the nitrogen and making nitrogen atom having more electrons to bond with the hydrogen ion. So increasing the number of alkyl group or electron donating group is one factor that makes available the lone pair of electrons on the nitrogen to bond with hydrogen ion. So we'll be going to the next question that has to do with organic synthetic routes. Organic synthetic route. That we will treat that in our next video. Thank you very much. Once more, fellow learners, if you haven't subscribed to our channel, please subscribe and do not forget to hit the notification bell. Coming up soon will be the next question. Thank you very much for watching.